So this is balanced iterative reducing and clustering using hierarchies. So in the BITS algorithm, we have two concepts like clustering features and clustering feature tree. So where the clustering feature is a triplet consisting of three parameters like n indicates the number of clusters and the linear sum of n data points, and the third parameter is sum of squares. So with the three parameters in the clustering feature, we can able to summarize the statistics of the cluster, and we can able to get the radius, diameter, etc., about the cluster. And we are also having in some additive property for this clustering feature. So where if you want to merge two clusters, we can get its clustering feature by adding the clustering features of the two individual clusters. And in the last class, we have gone through all these things. And these are the formulas for some of the distance measures. We're having centroid is there, and radius and diameter, where the radius is the average distance between the every point in a cluster to its mean, and whereas diameter is the square of average pairwise distance between the points of a cluster. And coming to the CF tree, here in the CF tree, we are having, we need to deal with the different parameters like branching factor and threshold, and one more parameter L is also there. So where if you consider the tree, so if you consider the CF tree, so what this branching factor explains about? So this branching factor explains about the, it tells that it's a threshold on number of, it is a threshold on the non-leaf node. It indicates the number of children, allowed children for a non-leaf node, right? If suppose branching factor is equal to 3, each non-leaf node should have only less than or equal to 3 children. Like that, it's a threshold on a non-leaf node. We're coming to the L. L indicates, L is a kind of threshold on a leaf node. So it indicates the number of subclusters in each leaf node. So if at all L is equal to 5, which means that each leaf node should consisting of less than or equal to 5 subclusters. Similarly, we have another threshold called T. So it's a threshold on a particular cluster in the, that means subcluster in the leaf node. So it indicates it's actually threshold on the diameter and the radius of a cluster. So this is all about the CF tree and how the insertion of a CF tree takes place, and all the remaining elements of the remaining things takes place regarding the CF tree in the sense. So if at all you are going to add an element to the tree, first we need to check with the root node, and really we need to traverse it to the last node, and based on its suitability, its similarity with the cluster present in the leaf node, it is going to be added to that particular cluster. So here, if at all, by adding that external record to the particular subcluster in the leaf node, if at all it obeys the threshold, then there is no problem. Otherwise, that cluster should be split into 2 subclusters. And after that, if at all it obeys the rule L, then there is no problem. Otherwise, the leaf node should be split into 2 leaf nodes. And again, we need to go back to the previous level. If at all that obeys the branching factor of the non-leaf node, then there is no problem. Otherwise, the branching factor, that means the non-leaf node should be split into 2 non-leaf nodes. In such case, the height of the tree may be increased by 1. So in this way, we are going to insert the elements into the CF tree. And as we have discussed in the last class, we have different phases of the BITS algorithm. Whereas in the first phase, we are going to load the tree. We are going to construct the tree by a single scan of the database in the first phase. And after that, we need to condense the tree into desirable range. And after that, we can construct the global clustering by merging the subclusters in the leaf nodes. And finally, we can make the refinement of the finally generated cluster. So these are the different phases. And here is an example. So if initially we are having a single cluster, right? So after that, by adding to some other incoming records, we can add that records to the existing cluster. So that depends upon the threshold of that cluster. Maybe it become a single cluster, or that is divided into two clusters. Like this, the CF tree is constructed. The CF tree is grown like that. So like this. So here, if you consider this example, for your sake of understanding, here is another example of construction of the CF tree and insertion of another new element into the CF tree. So if you consider this example, let us assume that the branching factor and the L value is equal to 3, which means that branching factor is equal to 3 in the sense it maximum allows only 3 branching factor in the sense. Here branching factor is equal to 3 in the sense it allows only 3 children. It allows only 3 children. Maximum of 3 children it allows. Here also L value is equal to 3 in the sense it allows only 3 clusters for a leaf node. Since here this is a leaf node, this is the leaf node and this is the non-leaf node. This is the non-leaf node and this is the root node. So here L is equal to 3 indicates each leaf node should consisting of maximum of 3 subclusters. So in this case, we are having 3 subclusters. Here we are having only 2 subclusters, and here we are having only 2 subclusters. So if at all we are having another element, some SC8 is there, some another subcluster is there, and according to the similarity measure, suppose it belongs to this leaf node 3. If suppose the subcluster 8 belongs to this leaf node 3, based on certain similarity measures, is there any need to update the tree or not? That means, is there any need to split the tree, split the node, split the cluster, or split the leaf node, or split the non-leaf node? Is there any need? If at all this subcluster 8 is going to be appended to the leaf node 3, is there any need to extend the tree? Anybody please respond. In such case, is there any need to extend the tree? Unnara? Respond ayya candidates. Number 1, 37, 49, 26. Present or not?
Yes, ma'am.
49 is there. ఏమైనా అర్థం కాలేదా లేదంటే లేట్ గా జాయిన్ అయ్యారా? If at all we are having a subcluster, SE8 is there. That is a new cluster, new incoming cluster. And by going through certain similarity measures, this subcluster belongs to this non-leaf node. Sorry, this leaf node 3. So I'm going to add this. I'm going to add this subcluster here. Is there any need to extend the tree? That means, is there any need to split this leaf node?
No, ma'am, no need.
Why? Your answer is correct. Just give the justification. So there is no need to split the node. There is no need to split this node. Why? Because here the L value for this node is 3. The L value that is the maximum allowed subcluster for that particular node is 3. So by adding this additional subcluster, it obeys the condition L rule. It obeys the L rule. So no need to go for splitting the leaf node 3. Whereas, but in this case, this subcluster is going to be added at leaf node 1. So here you can see here where it is going to be added to the leaf node 1. So in this case, what we need to do here?
We need to split, ma'am, because
we need to split the leaf node 1. We need to split. So what happens if you split the leaf node 1? Since these are the clusters actually, this is leaf node 1 and this is leaf node 2 and this is 3. Here additionally, subcluster 8 is added to the leaf node 1. So So according to the L rule, it shouldn't consisting of more than 3 subclusters. So it needs to be split into 2 leaf nodes. Then what happened? Additionally, some other leaf node is added to the non-leaf node 1, right? So here what happened actually? How many children are there for the non-leaf node 1? 4 children also. 4 children are there. Yeah. So given that L is equal to 3, this branching factor is also 3. So is there any need to split the non-leaf node or no need to split?
Split
Here
చేయాలి non-leaf node.
we need to split the leaf node. Why? Because
అదే
because
factor 3 కన్నా ఎక్కువ ఉంది కదా మ్యామ్ అందుకు.
Only 3.
Here it exceeds the limit. We need to split the non-leaf node into 2 nodes. So this is so what happens here? Automatically the length of the tree is extended by 1. So in this way we can make the insertion into the CF tree. So coming to the pros and cons of the Bitch algorithm, which performs faster than existing algorithms. So it scans the whole data only once. That means during the first scan of the database only, it can able to construct the CF tree. And it also handles the outliers much better, and it is superior to the algorithms in particularly in terms of stability and scalability. And coming to the cons of the Bitch algorithm, since each node in a CF tree can hold only a limited number of entries, due to the size, natural clusters cannot be formed. So here there is a limit for each limit for the number of entries, right? So natural clusters cannot be formed. Why? Because suppose here we have a cluster like this, and here is some other point. Here is some other point is there, but according to the rule, according to the threshold, according to the L rule, or not L rule. Suppose we are having some threshold. According to the threshold given, threshold defines some radius and diameter, right? According to the threshold given, this is only the allowed diameter for this cluster. So because of this particular data point, let us say this is X. This particular data point cannot be included in the cluster C. But in reality, this also belongs to that cluster because it is very close to that cluster. In reality, that is also belonging to that cluster. But we are excluding that. We are excluding that point. Why? Because we have a boundary based on the radius and diameter defined by the threshold. We are having a boundary. So we need to form the cluster by following that boundary only. So because of that, natural clusters cannot be formed. What is a natural cluster? So if at all it is a natural cluster, it needs to extend its diameter and it needs to include that X also. But this is not happened in case of this Bitch algorithm. That is one drawback. And another drawback is it cannot form that means here in this case, it only forms the spherical shaped clusters. It cannot form the arbitrary shaped clusters. Arbitrary in the sense, here is X. It cannot form cluster like this. Shapeless. It cannot form shapeless clusters. It only forms round shaped clusters. Why? Because it follows some radius. If at all you are having some radius in the sense, you can draw a circle with it. That means only spherical shaped clusters only it is going to form. It cannot form the arbitrary shaped clusters. So what happened with that? If at all you are having certain, just like the same example you can take. If at all you are having certain point, which is very nearer to that cluster, even though in that case we can't include that point into the cluster. Why? Because we can't generate the arbitrary shaped clusters. We can only go with the spherical shaped clusters. So these are all the drawbacks of the Bitch algorithm. And coming to the second algorithm of the multi-phase hierarchical clustering. So here we have two algorithms under that. First one is Birch algorithm and second one is Rock algorithm. So coming to the Rock algorithm, It's abbreviated as robust clustering using links. So just go through the name again. ROC in the sense robust clustering using links. Underline this word links. So something it considers the links between the elements of the clusters to generate the clusters. Instead of distance measures, something it considers links among the data points. So this belongs to the class of agglomerative hierarchical clustering algorithms, and it especially works for categorical attributes. Whereas till now all the clustering algorithms especially work for numerical attributes because they need to calculate the distance measures. Euclidean distance or a Manhattan or a Minkowski, whatever may be, they work mainly on the distance measures for the numerical data. So this particular clustering algorithm works for the categorical data. So we already have some techniques for calculating the distance among the categorical elements also, converting them into binary or ordered elements. We have already discussed all those in the previous classes only. So, but still we're having too many methods are there for handling the categorical attributes. This ROC algorithm expresses that even though we are having too many methods, too many ways of dealing with categorical attributes, they are not that much of efficient in case of calculating the similarity among the data points or clusters. So according to the ROC algorithm, the similarity among the data points, especially or clusters, in case of categorical attributes, can be computed with the help of links exist among the two records or two data points. So if at all if at all you go through the link concept, you can get more similar clusters rather than the previous concepts like ordering the elements or binary, dealing with the binary values, etc. So what is this link and how to deal with the links concept and how to calculate the similarity among the clusters by using this links concept, we will see. So here, this is the briefing about the ROC algorithm process. So here, first we need to obtain the random sample of the dataset. So here, first we need to obtain the random sample. We are not dealing with the entire data. We are just obtaining the random sample. And after that, we are going to cluster. We are going to apply some agglomerative. This is called as the link agglomerative approach. So this is the agglomerative approach. But here we are using links. That's why it is called as link agglomerative approach. So here initially we need to draw some random sample, and after that we need to perform the link agglomerative approach, and where the goodness measure, just reread the underlined terms. So if I have underlined something, they are something important, especially for this concept to understand. So we need to perform the clustering on the sample data using link agglomerative approach, where the goodness measure helps to identify the best pair of clusters to be matched. So what is agglomerative method? In agglomerative method, we are having some number of initial clusters. That means each point is considered as a cluster in case of agglomerative approach, right? And after going through certain number of iterations, we are going to merge the clusters. And that process is repeated until certain criterion exists, certain criterion satisfied. Like that, here also we need to go with the link agglomerative approach. And here we need to merge the best pair of clusters. And that best pair of clusters can be identified by going through the goodness measure. And after that, after having with the good number of clusters, what is the third step? We need to assign the remaining data points of the disk to the generated cluster. So initially we need to take some random sample from the data, right? Initially, we need to take some random sample from the data, and with that random sample, we need to generate some clusters by going through the link agglomerative approach. And after, once the clusters are generated, the remaining data is there, right? Out of 1000, initially you have taken only 500 as a random sample. Leftover 500 is there, right? So after, as a third step, the remaining data element should be assigned to the generated clusters in the previous previous phase. So in the previous phase, that means in the step 2, we have with some k number of clusters. So in the last step, the leftover data points are taken, and based on some suitability, each point should be allocated to the generated clusters. In such way, the entire database can be able to cluster. So this ROC algorithm can handle the data of any size. Why? Because initially it only takes a random sample. It does not go through the entire data set. So this is the advantage of ROC algorithm here. So for this, for understanding the ROC algorithm, we need to understand some basic concepts of the ROC algorithm, like goodness measure, what is this link, etc., etc. We need to understand first. So here we have some 5 basic concepts we need to go through. So before that, we need to know about the similarity function. That means how we can able to calculate the similarity among the data points. So here let's consider 2 points, P1 and P2. So since in ROC algorithm, we are going to treat each point as a cluster initially, right? So here similarity between the points, in this is similarity between the clusters. Here initially point and cluster same. So here particularly ROC algorithm uses Jaccard coefficient for calculating the similarity among the clusters. So it is defined with this formula. Jaccard coefficient is defined with this formula, and by going to this formula, we can calculate the similarity among the clusters. For example, you are having 2 records, for example. So what is the Jaccard coefficient here? P1 intersection P2. That means similarity between P1 and P2 can be obtained like this. P1 intersection P2 by P1 union P2. So how many common elements are there between P1 and P2?
2, ma'am.
So 2 common elements are there between P1 and P2. And how many total elements are there? What is P1 union P2?
7, ma'am.
7. Out of 7, 2 are repeated, right? Out of 7, these 2, faith is already here, right? Prayer is already here. So how many total elements are there in the sense? Judgment, faith, prayer, fair, and this one, 5. We don't consider these 2. Why? Because these are already repeated. So when you are going to consider the union of 2 sets, we no need to consider the repeated elements. So totally 5 elements are there. So this is the similarity obtained between the 2 records P1 and P2. 2 records or you can say it as 2 objects, or you can call it as 2 clusters, whatever. That is the similarity. So what is the similarity? This is 0.40. In this way, we can calculate the similarity among the 2 objects. But we are not, that means based on this only, we are not going to merge the clusters. Based on the similarity among the clusters, based on this, we are not only going, we are not going to merge the clusters. Beyond this step, we are going to find the links, number of links between the 2 clusters P1 and P2. This is the basic level, finding the similarity. So beyond that, on top of this, we need to calculate the links between the 2 clusters. Suppose P1 is a cluster and P2 is a cluster. We need to calculate how many links exist, how many links are there among the 2 clusters. If at all more number of links are there among the 2 clusters, we can say that those 2 clusters are similar to each other and we can match that. Then why we need to calculate this similarity using the Jaccard coefficient? In the sense, we need to calculate that links and to calculate that final selection of the cluster. So we need to have this result of similarity. We need to have this result. So based on this value 0.40, we are going to take the next step. That's why we need to calculate this here. So whereas in case of previous clustering algorithms, we are just going to calculate the similarity in terms of Euclidean distance or whatever. Based on that, we can judge which 2 clusters can match together like that. But here, this is not like that. Here, the case is different. We are not going to match only based on the similarity. Along with the similarity measure, we are going to proceed with calculating the number of links between the clusters. So what is that link and how to calculate the links among the clusters? For that, we need to know about the neighbors. We need to know about the neighbors. Why? Because here link is nothing but link for a pair of points is the number of their common neighbors. So how a link is defined? Link among the pair of points is nothing but the number of common neighbors. Suppose you are having a point here and here a point is there. This is P1 and this is P2. If you want to know how many how many links are there between the clusters or between the points, we need to know about the common neighbors. How many common neighbors are there? Suppose here is some other point, some Q. This is a neighbor. This is a common neighbor actually. This is a common neighbor for P1 and P2. So like this, how many common neighbors are there? That is equal to that number of links exist among P1 and P2. Why? Because I can draw a link between these two and I can draw a link between these two. So I can say that link is nothing but link among 2 points, nothing but it's a length of 2. It passed by it covers a common neighbor. Link is nothing but it's a length of 2. Why? Because this is length of 1 and this is length of 2. Totally, a link among the 2 points is nothing but a length of 2, and it bypasses a common neighbor. Suppose here also we are having some Z is there, some other point is there. This is also a common neighbor, for example. So you can also draw a link for these two. This is 1 and this is 2. Length is 2. So this is the first link. That means this is the first common neighbor and this is the second common neighbor. If suppose only 2 common neighbors are there, we can say that there are 2 links among P1 and P2, like that. So before going to the link, we need to know the number of common neighbors exist among the points. So here coming to the neighbor count. So if similarity between 2 points exceeds certain similarity threshold, they are neighbors. So how I can decide Q is a neighbor of P1 and P2 and Z is a neighbor of P1 and P2? How I can decide that? For that, I need to calculate the similarity between, for example, let me change the color. Suppose I can say that Q is a neighbor of P first. Just ignore about the common neighbor. First, I need to say that Q is a neighbor of P1. And again, I need to calculate whether it is a neighbor of P2 or not. So how I know that Q is a neighbor of P1? For that, I need to calculate the similarity measure. That means similarity of this P1 and Q I need to find out first. How to find out the similarity among 2 points? That we already know that. Here we have some formula taken from Jacob coefficient. So with this, we need to calculate the similarity among 2 points. If this similarity satisfies a given threshold theta, if this satisfies a given threshold theta, exceeds 2 points exceeds certain, that means it should be greater than this theta. If at all this happens, I can say that the point Q is a neighbor of P1 or P1 is a neighbor of Q. Similarly, I need to calculate the similarity among this P2 and Q. If this is also satisfies some threshold, that I can say that Q is a neighbor of P2. So from these 2 steps, I can observe that Q is a neighbor of both P1 and P2. So I can note down that Q is a common neighbor. So one common neighbor I have identified just now. Like based on the similarity we have calculated in the previous slide, we can take that formula and based on that you can able to identify the number of neighbors first, and after that you can able to identify the number of common neighbors, and based on that common neighbors you can able to identify the number of links exist among the pair of points or exist among the clusters. So here intuitively it is the number of coming to the link, it is the number of distinct paths of length 2 that we have already discussed just now that exist between a pair of points. So note that a point is considered as a neighbor of itself as well. So we can also say that B is a neighbor of itself. B is a neighbor of itself. Like this, you can also say that. And here, if a point has X neighbors, for example, if at all a point has X number of neighbors, then we can say that there are approximately X power 2 number of links. I can say like that. Suppose here, how many neighbors are there for R? In this example, in this picture, how many neighbors are there for R? R consisting of 3 neighbors, A, B, and C. From this figure, I can get that. R consisting of 3 neighbors. So how many links, possible links are there for R?
3, ma'am.
How many possible links are there?
3 square, ma'am.
Yes, 3 square. Why? Because here, if at all there are 3 neighbors, we are having 3 power 2 links, possible links. So all these are the possible links for a particular value, particular point. So what are all those links? A, B, A or B. This is a link, and this C or B is a link, and sometimes here A or A is also considered as a link. A or A. All these are allowed links. All these are allowed links. That is not the fixed value. All these are maximum links we are having that. And within that, which are actually possible in that particular example, that we need to find out. So if at all a point has X number of neighbors, the maximum possible links are X per 1, like this. And here consider another example. We're having 3 points are there, and here certain data is given. The neighbor of P1 is P1, P2. Neighbor of P2 is P1, P2, P3, and neighbor of P3 is P2 and P3 and P2. So how many links are possible in between P1 and P3? How many links are possible in between P1 and P3? How we can able to know that? Link is nothing but number of common neighbors, right? So how many common neighbors are there in between P1 and P3?
One, ma'am.
Only one. That is what?
P2.
So P2 is a common neighbor. Since only one common neighbor, how many links are possible among P1 and P3?
One, ma'am.
One. Since we have one common neighbor, one link is possible. Like that, you can identify the neighbors, and thereby you can identify the links. And here is a next concept we need to know under this ROC algorithm, that is criterion function. So to get the best clusters, we have to maximize this criterion function. Some criterion function is there, and there the Ci denotes the cluster, particular cluster I, and Ni is the number of elements in that cluster, and K is the total number of clusters possible for a ROC algorithm, and theta is the similarity threshold. We already know that. And here this function of theta is given like this. So here by maximizing this criterion function, which consisting of some sigma indicates the addition of number of links between the 2 points. That means it adds the number of links between 2 points in a cluster. That means indirectly it tries to maximize the number of links within the cluster. So by maximizing this criterion function, we are maximizing the sum of links of intra-cluster. Intra-cluster is within the cluster. Within the cluster pairs, and at the same time minimizing the sum of links among pairs of points belonging to different clusters. So if at all points within the cluster should have maximum number of links, and all points within the cluster and outside the cluster, that means the number of links between the points of the cluster, that means here all the points, link between all the points within the cluster should be as maximum as possible, whereas link between the point within the cluster and the point outside the cluster, suppose here also we are having a point, these kind of links we should reduce as minimum as possible. We should form the links. So this criterion function maximizes intra-cluster links. That means links within the cluster it maximizes, and it minimizes the inter-cluster links. That means cluster to cluster. Suppose this point belongs to another cluster. There shouldn't be any link between the clusters. If at all there is a link, that point is also added to this cluster, or this point is added to this cluster. But there is no link between the clusters. Intra-cluster link should be there, but intercluster link should be reduced. That can be done by maximizing this criterion function. So here is a goodness function, goodness measure we have already discussed in the slide 1 of this ROC algorithm. So during clustering, we use this goodness measure in order to maximize the criterion function. So this goodness measure helps to identify the best pair of clusters to be matched during each step of the ROC algorithm, where this value we have already taken from here. F of theta is equal to 1 minus theta by 1 plus theta. So coming to the briefing of the ROC clustering algorithm, first we need to draw the random sample from the dataset, and next sampling is used to ensure scalability to very large datasets. Why scalability here? Why we are going to take the sample? If the dataset is too large, it's difficult to form the clusters, difficult to process the entire data. That's why in the ROC algorithm we have considered the sample of the dataset. So the initial sample is used to form the clusters that we already know. Then the remaining data on the disk is assigned to these clusters. After formation, the remaining data is also assigned to these clusters. 3 minutes left to this. So next, perform a hierarchical agglomerative clustering algorithm in the step 2. So ROC performs the following steps which are common to all agglomerative algorithms. So how to perform clustering? Here, first step is it places each single data point into a separate cluster. Since it follows some agglomerative algorithm, each data point should be placed in a different cluster. And next, compute the similarity measure for all pairs of clusters. So next, we need to find out the similarity measure for all pairs of the clusters. So how to calculate the similarity measure? Based on the Jaccard coefficient. And after that, we need to calculate the neighbors. And after that, we need to calculate the links among the points or clusters. And based on the links only, we can merge the clusters. So similarity measure include all these things. So merge the two clusters with the highest similarity. So that is based on the goodness measure. So verify a stop condition and you can repeat the process until the stop condition reaches. And after that, finally, after clusters are constructed, finally the remaining data points in the disk are assigned to the generated cluster. So this is done by selecting a random sample from each cluster. Then we assign each point to the cluster for which it has the strongest linkage with that point. For example, we have some generated clusters. 4 clusters are finally generated. And we have certain points here. So how to assign? Suppose P is there, Q is there, R is there, S is there. How to assign each point? How to know which point belongs to which cluster? Here we are having different resulted clusters, finally generated clusters. So what they are telling is just randomly take some point in the cluster. So out of this cluster, take some random point and calculate the similarity between these 2 points. If at all it is similar to this point, you can assign P to this cluster C1. Similarly, you can take random point from here also, and you can take some random point, and you can random point, not the centroid or not some other specific point. You can take randomly one point, and you can calculate the similarity between this particular point and all other random points chosen from the cluster. Based on that similarity value, which value is much similar. So for that cluster, the P needs to be assigned. Similarly, for each other point which is taken from the disk, for all the points, the same procedure can be followed. Like this, ROC algorithm assigns the data to that. So coming to the computation of the link. So using the similarity threshold theta, we can convert the similarity matrix into an adjacency matrix. So actually, this is the process we need to go through. But for the large set of data, it is not possible to go through each and every observation specifically. That's why how we can generate the links in the sense. First, we need to generate the similarity matrix. So using the Jaccard coefficient, we need to generate the similarity matrix. And based on that similarity matrix, you need to generate the adjacency matrix. Based on that, you need to generate the adjacency matrix. And after generating the adjacency matrix A, you need to square the adjacency matrix with itself. You need to perform this A square. So this resulted matrix can be referred as a link matrix among the 2 clusters. So this will be explained with an example in the next class. Probably today afternoon, 2 to 2:50 class is also DWDM class. Prepare accordingly. And let me know the attendance. ఎంతమంది వచ్చారు? అటెండెన్స్ చెప్పిన వాళ్ళు లీవ్ అయిపోవచ్చు.